we're finally ready to show that if we take a linear map, it can be represented by a matrix. So for any map T from between V and W, there's a certain matrix that does precisely what T does by T of V equals A times V. Okay? And this idea is, we're going to break it into two parts. The first part is going to be a theorem that says that this can be done. Okay? And we're going to write the theorem, we're going to give an example, we're going to prove the theorem. So that's going to be the first part. That's going to be this clip, showing that it can be done. The second part is, how do we do it? Somebody gives you a linear map, you're not going to say, hey, this can be done. You want to actually do it. You want to produce that matrix. You get T, you want to produce A. And that's the idea of how to do it is in fact hidden in the theorem, and that's going to be the next clip. How we do it, how we actually produce the matrix that represents a given linear transformation. Okay? So part one, the theorem. So here it is. In fact, the actual statement is going to be a corollary of the theorem. So you're not going to see it yet. You're going to see it at the end as a corollary. So let V and W be vector spaces. The only thing we're going to need to require in order for everything to compile is that they share the same field as the field of scalars. Okay, that's throughout any statement on linear transformations, right? Vector spaces over the same field F.
Can't the linear map change the...
No, it doesn't compile. We talked about it when we defined the linear map. What is T of V? What is T of alpha V equals alpha T of V? Okay, if alpha doesn't live in the same place, you can't pull it out. It doesn't make sense at all. Okay, so let B equals V1, V2, up to Vn be a basis for V. So V is going to be a space of dimension n, and B is a specific basis for V. And let A, which I'm going to denote by W1, W2 through Wn, these are little v's, these are little w's, be any subset of W. So there are no assumptions on A. Not that it's a basis, not that it's even spanning or linearly independent, nothing. Just n vectors in W. Okay? But the only thing is that I'm taking the same number as the basis of V. Okay? Why? So this is going to be the reason. Define T of... So I want to define a linear transformation between V and W. Okay? I have a basis, B, for V. So any element in V is a linear combination of these basis elements, right? So in order to tell you what T does, in order to define a linear transformation, I have to tell you what it does to every element in V. So I'm going to write that element in V as a linear combination of these. Alpha 1 V1 plus alpha n Vn. This is a general element in V, looks like that. And I'm going to define it to be, here's the definition of T, I'm going to define it to be that exact linear combination of the little w's. Alpha 1 W1 plus dot 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 alpha n Wn. That's the definition of T. That's how I'm defining T. Do you agree that it's defined now for every element of V? Okay. Then, there are three statements. One, T is a linear map. This requires proof. I just told you what it does. Why is it linear? Okay, you have to show it. You have to show that T of V plus T of U plus V is T of U plus T of V, and that alpha T of V is T of alpha V, right? You have to prove it. That's part one. Two, if this set A in W was not just any random collection of n elements in W, but happened to be a basis for W, then T is not just a linear map, it's one-to-one and onto. If A is a basis for W, then T is one-to-one and onto. And three is the statement that this T, this specific T is specific in this theorem. It's the transformation that does this. T is the unique map, the unique linear map. Obviously, it's not the unique linear map from V to W. You can take many of those, but it's the unique map that does something, okay? Such that T of Vi equals Wi for every I. So if you want a map that maps V1 to W1, V2 to W2, Vn to Wn, there's only one map that does that precisely, and it's this T, given by this formula. Okay? So these are the three statements of this theorem. What I want to do is first give you an example, show how these ideas build up. Okay? Before we even, and then I'm going to make a few remarks, and then we're going to prove it. So first an example. So let's find a map from R2 to R3. So this is V, this is W. They're not of the same dimension. There was no claim that they are. Okay? So we're going to find the map such that I want it to perform in a specific way on R2. I want to prescribe what it does to the standard basis of R2, such that T of 1, 0 equals, I want to tell you precisely, I want to declare what it does to 1, 0. I want it to be root 2, negative 1, and E. I want this to be what T does to 1, 0. And T of 0, 1, I want that to be 1 pi 2. Suppose I want to find the map that does that to the standard basis of R2. Okay? How do I do it? Here's the idea. How do I do it? I take a general element in R2. What's a general element in R2? It's some AB. That's what a general element in R2 looks like. Do you agree? Okay. I write it as, so in order to prescribe T on all of R2, I have to tell you what it does to AB, right? So I write AB as A times 1, 0 plus B times 0, 1. This is a basis. I can always write it as any element is a linear combination of the basis elements. Do you agree? And throughout this example, think R17 and matrices or whatever. You can see that this works in general. If you take a general element, you can write it as T of a linear combination of the basis elements, right? There's nothing special about R2 here. Okay? That's going to be the idea of the proof in a minute. Okay. This equals, I want T to be a linear map. I want it to be a linear map. So T of a sum is the sum of the T's, and then I can pull out the scalars. So that's going to be A times T of 1, 0 plus B times T of 0, 1. If T is going to be linear, then it's going to satisfy this, right? And therefore, this is going to be equal, since I just told you what I want T to do to the basis elements, That's it. It's going to be a times root 2 negative 1 e plus b times 1 pi 2. Do you agree? What we showed so far is that if you want to take a linear transformation and you want to force it to do something to basis elements, it forces what t does to any general elements. Defining t on a basis fixes t. T doesn't have any choice. For any vector ab, that's what it's going to have to do to it. Okay? Furthermore, once we write it like this, I can rewrite it as 1 pi 2. Let's take an intermediate step. I can write it as a root 2 plus b, negative a plus pi b. Do you agree? And a e plus 2b. This is t of ab, precisely. Do you agree? And furthermore, I can rewrite this as, tell me if you agree, root 2 negative 1 e 1 pi 2 times ab. So it's root 2 times a plus 1 times b. That's the first element. Negative a plus pi b. That's the second element. And ea plus 2b. That's the third element, matrix multiplication. Do you see that? So when I tell you what t does to basis elements, in fact, I fix t. There's only one t that's going to do it for the entire space. And it's in fact given by a matrix. The matrix is a matrix whose columns are t's of the basis elements. Do you see that? Okay, so there we have it. We just started with a transformation that was prescribed on basis elements, didn't have any matrices involved in it, but suddenly it showed up as a times v. T of v is in fact a times v. Do you agree? Okay, so this is a matrix. Let's write columns are t of the ei's. Right? If this was E1, and this is E2, then the columns are t of E1 and t of E2. Do you see that? Okay. So we're going to keep this example in mind as we go through the theorem and get to the conclusion, the corollary of the theorem, that given a map, you can always find a matrix like this. Okay. So let's go, questions about this example. Did everything that happened make sense? Okay. So let's go back to the theorem. What's the statement? Let's start with part 3. Well, part 1 is that you take a linear transformation, define it on a linear combination as a linear combination, and it's a linear map. This is going to require just working with the definition, 3 lines of technical calculations, completely basic, and it's going to prove it. There's no issue in part 1. Okay? Part 2 tells you that if you're sending a basis to a basis, then the map is going to be one-to-one and onto. Okay? That's already hinting at something we're going to say later, that a linear transformation is one-to-one and onto if and only if the dimensions are the same. We already hinted at that previously. So this is really laying the ground for things to come. Okay? What's important for us is part 3. Okay? Part 3 here says that this T, which was precisely what we did in the example, is the unique map that is prescribed by what it does to the basis elements. Okay? You pick the images of the basis elements, whatever you want. T of V1, you want it to be W1. T of V2, you want to call it W2. Whatever you want. A priori, there's no claim on the W's. Whatever you want, that fixes T. Okay? Good? Okay. So let's write that as a remark first. Let's write that as a remark first, and then we'll prove the theorem. So remark. 3 of the theorem means the meaning of part 3 is that if we take a basis B for V and define what, I'm going to write it in kind of a non-formal way, and define what T does to basis elements. Right? So that B was V1 through Vn, and I want to fix what T of V1 through T of Vn is. That's the Wi's. Then this determines T. It fixes T. There's only one T that does that. Okay? How? T of alpha 1 V1 plus ... alpha n Vn, right? V1 through Vn are the basis elements. Take a linear combination, that's a general element, just like in the example, AB. Okay? It's precisely alpha 1 T of V1, which was the W1. Okay, so it's precisely the linear combination of the images. Okay? Good? If you take a basis and prescribe what T does to the basis elements, it fixes T. Good? Okay, so let's prove this theorem. Okay, so proof of theorem. So what did the theorem say? Let's look back at the theorem. We have two spaces, V and W. We have a basis for V, and we have some n elements in W, any n elements. Okay? We're defining T of an element in V. Any element in V is a linear combination of the basis elements. We're defining it to be the same linear combination where we replace the V's with the W's. Okay? The same linear combination of the W's. Part 1 says this is a linear map. Let's show that it's a linear map. Okay? By definition. So part 1, I need to take two guys in V. Let's call them U1 and U2. And I have to show that T of their sum is T of U1 plus T of U2. Right? That's the first part of showing the map is linear. So what is T of U1 plus T of what is T of U1 plus U2? U1 was some linear combination of the little v's. Right? It's an element in big V. B is the basis for that. So U1 is some alpha 1 V1 plus ... alpha n Vn. That's U1. And U2 is some other combination, beta 1 V1 plus beta n Vn. Do you agree? That's two general elements. They're linear combinations of the basis elements. Okay. Okay. Can I break this into alpha 1 T of V1, etc.? Can I do that now?
We don't know it's a linear map.
Right. That's what we're trying to prove. Right? We're trying to prove that it's a linear map. So we can't just say, like we've been saying several times when we were working with linear maps, that this equals alpha 1 t of v1 plus alpha 2 t of v2, etc. That's what we're trying to prove. We can't do that. Right? Good? Is the logic clear? Okay. So what we can do is we can rewrite this as t of alpha 1 plus beta 1 v1 plus alpha 2 plus beta 2 v2. That's just collecting these guys in the order of the v's, right? There's alpha 1 v1 and there's beta 1 v1 here. Then there's alpha 2 b2 and then there's beta 2 v2 here. So I can write this Do you agree? Okay. And now what I do know is I know how t is defined. T is defined by sending each a linear combination like this to the exact same linear combination of the w's. So by definition of t, this equals alpha 1 plus beta 1 w1 plus alpha 2 plus beta 2 w2 plus dot 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 alpha n plus beta n wn. That's the definition of t. Right? Okay. Now this I can now break as alpha 1 w1 plus alpha n wn plus beta 1 w1 plus beta n wn. Right? And this is precisely t of alpha 1 v1 plus alpha n vn. That's how t is defined. Do you agree? Plus t of beta 1 v1 plus beta n vn. Good? Okay, so t was really constructed to be linear, and it happens to be linear. That's basically the statement. So this is t of u1. Oops. So that's the linearity. We proved it. Good? Okay, so show that t of alpha u equals alpha t of u. That's the second part of being linear. Very similar manipulations like this show it. Okay? So that proves part one. If you define a map T of a linear combination as the same linear combination of some elements in the range, what you get is a linear map. Good? Okay, let's prove part two. So part two, I don't want to, okay, let's erase here.
Did you take a U1 and U2 that they're not equal to V1 to Vn?
U1 and U2 were any general elements in the domain space V. Each element in the domain space is a linear combination of the basis elements of the domain space. Okay, so U1 was some linear combination. I called it alpha 1 V1 through alpha n Vn, and likewise for U2, beta 1 V1 plus. Okay? Okay, so part two, the claim is that if A was not just any collection, random collection of n vectors in W, but a basis for W, and T is defined as such, then it's a one-to-one and onto linear transformation. Okay, so let's prove that. T is one-to-one. Let's show that first. So the way to show that a transformation is one-to-one, you should already feel by this point that showing that a map is one-to-one, how do you do it?
Kernel is 0.
Right, show that the kernel is 0. Okay, so how do we show that the kernel is 0?
So that it's
We take somebody in the kernel and show that it's only 0. Okay, so let U be some element in the kernel. Some element in the kernel. Okay? What does it mean that it's an element in the kernel? It means then that when we t it, what do we get? 0. That's what it means to be in the kernel, right? On the other hand, what is t of u? Just like before, u is some linear combination of the basis elements, so it's alpha 1 v1 plus alpha n vn, right? And by definition,
The same with W.
it's alpha 1 w1 plus alpha n wn. That's the definition of t. That's what t does. It takes a linear combination and gives the exact same linear combination with w's instead of v's. Okay? So what do we have here? We have a linear combination of the w's, which equals 0. But now we're assuming that these w's are a basis. That's the assumption of part 2. Okay? So if we have a linear combination that equals 0, what are all the alphas?
0.
Right. So since A is a basis for W, A was W1 through Wn, alpha 1 equals alpha 2 equals alpha n equals 0. All the coefficients here are 0. But if all the coefficients here are 0, that's these alphas. So U is in fact 0. So therefore, U is 0, and therefore the kernel is trivial. Okay? If the kernel is trivial, T is 1 to 1. Good? Okay, now we need to show that T is onto. This can be argued directly. Okay, and in fact it's a one-liner directly, but can you tell me how to show that T is onto, not in a one-liner proof, but in a half-liner proof?
No, rank nullity theorem.
The corollary of the rank nullity theorem, right? We're assuming that A is a basis. So let's look at the theorem again. We're assuming in part 2 that A is a basis. So B is a basis for V, it has n elements. A is a basis for W, it has n elements. So these two have the same dimension, right? If they have the same dimension, and the map is 1 to 1, then it's also onto. That was a previous corollary, just in the previous clip. Do you remember? Okay, so let's write that. Since dim V equals dim W, that's our assumption in part 2, and T is 1 to 1, T is also onto by a previous theorem. A map, a linear map between two spaces that have the same dimension is 1 to 1 if and only if it's onto. Good? Everybody? Okay. Let's prove part 3. By the way, it's worth giving it a thought how to prove this without pulling this from your sleeve, right? This is heavy artillery here. You can prove that T is onto directly by the definition of T in this case. It's very easy. Try to think of how to do it. Okay? Not now. Later. Try to think of how to do it. Let's prove part 3. So part 3 is the claim that the way T is defined as sending the linear combination of a given basis to the same linear combination of any chosen subset of the range, it's the unique map that sends the VI's to the WI's. Okay, so let's prove that. And this is not under the assumptions of part 2. Part 2 started with the word if. We're again not assuming that A is a basis for W. Okay, we're back to the general situation. So if T of VI equals WI, Okay, so we're assuming that we have a map that does that. We want to show that it can only be the map from the theorem. Okay, then what is T of alpha 1 V1 plus alpha n Vn? So if T of Vi equals Wi and T is linear, we're assuming that we have a linear map that does that, and we want to show that it's precisely the T from the theorem. Okay, so if T is linear and does that, then what is T of a linear combination? We already know. It's alpha 1 T of V1. Now we're using the fact that T is linear plus alpha n T of Vn, right? And therefore, it's precisely alpha 1 W1 plus alpha n Wn. Good? So a linear map is determined by what it does to basis elements. Good? Okay, so finally, here's the corollary. What we really want.
Doesn't it suffice to say that it's one-to-one and onto? Well, it's implicit once you say it's one-to-one and onto.
What's implicit?
The theorem.
No, but the third part is not related to the second part.
Oh, you're proving in.
The second part starts with the word if. Okay, the third part is not under the assumption that the if of the first part is satisfied. It's general. Okay. Okay, so corollary, and this is what we were interested in. Any T from Fn to Fm. Okay, so any T where the V and the W's are, well, we're thinking of them at first as column spaces, okay, but later we're going to see how to generalize this to any T from V to W, but at first, from just Fn to Fm, that's what's going to follow from that theorem, any T, any linear map, any linear map T from Fn to Fm is of the form T of V equals A times V for some matrix A. And A is going to be of size m by n. Okay? Why is that true? So proof. Idea, do precisely what we did in the example. Let's look at the example again. We had a linear transformation from R2 to R3. Okay? It's determined by what it does to the basis elements. So do T to the basis elements, you get these two, set them as columns, that's your A. That's the proof. That's going to be the proof. Okay? And the details of why this works in general and not just in this example are in that theorem that we just proved. Okay? So let's do that. Let E1, E2 up to En be the standard basis for the domain space Fn. Okay, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, all the way up to 0, 0, 0, 0, 0, 0, 0, 1. Okay, remember what the EIs are? Okay. Denote T of EI equals WI. T now is given. I don't know anything about it. except the fact that it's a linear map. Okay? So T does something to E1. Call that something W1. T does something to E2. Call that something W2. T does something to any EI. Call that something WI. I don't know anything about the W's. They're just the T's of the basis. Okay? So this is going to be the basis B. And this is going to be the set A in Fm. Good? Okay. By the previous theorem, so we have what is T of any element V in Fn. I can write V as a linear combination of the basis for Fn. So it's T of alpha 1 E1 plus alpha n En. Any vector in Fn can be written as the linear combination of these basis elements. Right? Okay. This equals, we know that if T does this, then it's fixed on any element, so it equals alpha 1 W1 plus alpha n Wn, right? Because this equals alpha 1 T of E1 plus alpha 2 T of E2 plus alpha 3 T of E3, and each of those are precisely the W's. Good? Okay. And this equals, just like in the example, these are the, let's look at the example again. In the example, we're now at this point. This is W1, that's T of E1. This is W2, T of E2, right? And T of V is alpha 1 W1 plus alpha 2 W2. And that equals A times V, where A is the matrix whose columns are the W's. Okay? So let's write that. That equals A times V, or we can write it explicitly. Okay, let's write A is the matrix whose columns are the W's. So W1 is an element in Fm, right? It has M components. Let's call the components of W1, W1, 1, W2, 1, all the way up to Wm, 1. Those are the components of W1. Okay? And the components of W2 are going to be called W1, 2, W2, 2, all the way up to Wm, 2. And so on, all the way up to the components of Wn. I'm going to call them W1n, W2n, all the way up to Wmn. Right? And I'm going to multiply that by V. What is V? V is alpha 1 E1 plus ... alpha n En. So V is precisely this vector. Alpha 1 through alpha n. Right? So multiply, you get this times this, and this times this, and you can spell it out. It's precisely this linear combination. Okay, so these are, let's write that in blue. So the columns of A, where the columns of A are the Wi's. Okay, so any map from Fn to Fm can be presented by a matrix A whose columns are the images of a basis for Fn. Okay? Just like in the example. So first verify that you understand the example, which is the simplest case, and then see that you can write this in general. Good? Everybody good? Okay, so I can see in your eyes that some of you are good and some of you are a bit lost. Lost, whenever you see something like this, it makes you a bit whoa. But go back to the example. See what happened in the example. It's precisely the same thing. Precisely. Letter to letter. Okay? Except that there, this was only had A and B rather than alpha 1 through alpha n. And therefore this had only two columns, T of E1 and T of E2. And E1 was 1, 0 and E2 was 0, 1. And that's it. Okay, so everything was a lot simpler in the example, but the idea is precisely the same idea. Okay, good. So what I want to do next, but we're going to separate it. We're going to do it in a separate clip. What I want to do is show this in even further generality. I'm going to take a vector space V here and a vector space W here, assume nothing about them, and show how to construct the matrix which performs just this. But the matrix is not going to act on this itself, the coordinate vectors. Exactly. Okay, because if this is a space of polynomials, I don't know how to multiply a matrix by a polynomial. It doesn't make sense. AV, where A is a matrix and V is a polynomial, doesn't compile. But if V is the coordinate vector of the polynomial, it's going to be somewhere here, and A is going to know what to do with it. And it's going to send it precisely to something here, which when I translate back to polynomials is going to be what I want. Okay? So that's coming up next.